Okay, so today's lecture is about daylighting and also the Sunpach Diagram. And next week, I will be here also, and we will learn something about the lighting fundamentals and indoor lighting. Okay, so for today, about natural lighting, okay, natural light. And then next week, artificial lighting. Okay, so this week I have prepared 2 tutorial questions, or maybe 2 example, 2 exercise. So let us finish all these 18 number of PowerPoints, and then we will study the tutorial questions. Okay, so sunlight and skylight. So we all know what is the sun and what does it mean by sunlight. Okay, so the sun is the origin of life. So the energy of sunlight supports almost all life on Earth by photosynthesis and drives the Earth climate and weather. So without the sun, we all will not be here. There will be no living things on Earth. So the sun is super important, and that's why you may aware that there are many religions which worship the sun as the god. Like we have the Apollo, the son of the god, and then the Egyptian, they have the god called Ra, which is also the sun. Okay, so for this lecture, we will study how the sun moves across the sky and how can we estimate the position of the sun relative to the Earth. And we will also learn to use a Sunpach diagram, which can examine the sunlight availability of a interior flat. Okay, so apart from sunlight, which reaches the Earth directly, light is also received indirectly as skylight. Okay, so we have a atmosphere. And the atmosphere consists of many different types of gas and water vapor. So these gas will absorb and re-emit the light. Okay, so without the sky or without the atmosphere, it will be very cold at night, and then in the daytime we have a very strong sun. Okay, but now we have the atmosphere. So apart from the sun, which is the light source, the sky, the whole sky hemisphere is also a light source. So we call the light comes from the sky to be skylight. Okay, so in this diagram, we use a hemisphere to represent the sky. Okay, so this is for presentation and also for calculations. Okay, we assume the sky to be a hemisphere. So the Earth's atmosphere consists of a huge number of air molecules. They absorb light and then quickly re-emit in different directions that light had been traveling, such that light scatters in all directions. Okay, and this scattering process is more efficient for short wavelength. Okay, short wavelength, which is the blue color. Okay, so it means that this scattering, the blue light scatter more compared to the red light. So the blue light is scattering everywhere along the whole sky hemisphere. And that's why the sky is seen to be blue in color, but not red. Okay, because blue light is more effective in scattering. So you may wonder, so I know that daylight or sunlight consists of a wide range of wavelength. So from red color all the way to the violet color. That is what we see in the rainbow, right? A spectrum. So it means that the violet color will even have a shorter wavelength than the blue light, right? And it means that shorter wavelength, the violet light should scatter even more in the sky hemisphere. So then why not the sky being violet color? So one reason is that our eyes is not sensitive to the violet color. And we are a little bit more sensitive to the blue color. So for the sky, it is a little bit violet color, but we cannot see it. Okay, we cannot perceive those violet color. So we are more sensitive to the blue, green color. And that's why we see the sky being blue. And in the sunset and sunrise, because the red light is less sensitive to the scattering. And that's why the sunlight, the red light, can enter to our eyes directly, and we see the sun in the sunrise and sunset being red in color. Okay, so I want you to understand that for the natural light, we may divide them into two portions. The sunlight, which is the light directly come from the sky, directly come from the sun. And we have the skylight, which is the light comes from the sky. And these skylight are diffuse. Okay, so what does it mean by diffuse? For sunlight, is it direct? And for skylight, it is diffuse. So when the light is diffuse, it means that it will come from all direction. Okay, so for direct light, there will be shadow. So under a sunny sky, you will have your own shadow, right? When you are outside, then you can see your own shadow. But when it is diffuse, when it is cloudy, okay, when it is very cloudy, no sunlight, then you have no shadows because light comes from all direction. So diffuse light. And we may also have reflected light. Okay, so under a clear sky, okay, very sunny, you have the strong sunlight, and then you are staying in the shade. Okay, you are staying in the shade. Will you get your skin tanned? I mean, you have the UV light, right? So when our skin is exposed to the UV light, our skin will get, with the color of our skin will get darker. So when you are staying in the shade, okay, you are hiding, you are hiding away from the sun, will you still get your skin tanned? Yes, it's because of the skylight, okay, and also the reflected light from the sun, and also the reflected light from the sky. Okay, so this is just a concept about how we categorize the light comes from the sun, from the sky. We have the direct, we have the diffuse, and also reflected light. Okay, so just some basic concept. And the sky type. Okay, so cloudy, sunny. And for cloudy sky, when it is heavily cloudy, okay, the cloud completely obscures the sky. So you will not be able to see the blue sky. Okay, the whole sky covered by thick cloud. Then it is called overcast sky. Okay, so under the sky, you have no shadows, and it produces diffuse light only. Okay, no shadow, only diffuse light. And the opposite to overcast sky will be clear sky, and the sun is the brightest source of light. No cloud, just the sun and the blue sky. And the clear blue sky provides low illumination. So this is a new term, illumination. And illumination actually means light. Okay, so if you can block the sun, then just the blue sky will produce less light, or not a very high output of light. Okay, so comparing to the overcast sky, the blue sky will be darker. Okay, so for the overcast sky, it could be very bright. Okay, it could be very bright under the overcast sky, but for the blue sky, it provides low illumination. Okay, but of course you have the sun. The sun is very, very strong. Okay, it has a very high intensity. So the adding component, the adding illumination, or the summation of the illumination due to the sun and due to the blue sky must be larger than that of the overcast sky. But if you only study the sky component, okay, the blue sky illumination and the overcast sky illumination, usually the overcast sky will be even brighter than the blue sky. Okay, so in between overcast sky and clear sky is called the partly cloudy sky. Okay, so I think it is very easy to understand, right? So between the two, so the cloud is not thick and it didn't cover the whole sky. So you still have a bright sun and part of the sky covered by the cloud, which is, we call that the partly cloudy sky. Okay, later on, when we study a parameter called daylight factor, we need to have a clear understanding of the sky types because daylight factor is a term only for overcast sky. Okay, we will talk about that later on. So first of all, let's discuss why do we have seasons. It is now March, okay, so it's now spring. And for Hong Kong in July, in August, it will be summer. And then in December, it is winter. Okay, so we have different seasons. Why do we have seasons? Is it because the Earth revolves around the sun in an eclipse, not a perfect circle? Is it because of that reason? No. The Earth's ecliptic orbit around the sun has very little effect on the seasonal difference in weather. We have seasons is because the Earth axis is tilted. Okay, the Earth axis is tilted. So on the plane where the Earth revolves around the sun, the North Pole to the South Pole, this axis is not perpendicular to that plane. Okay, we have the Earth revolving around the sun, and this pole is not perpendicular to that plane. Okay, so this plane, this is the plane where the Earth revolves around the sun. And the axis has a certain tilting angle, which is 23.45 or 23.5 degrees. So the Earth rotation tilts around 23.5 degrees on its pole-to-pole axis relative to the plane of Earth's solar system orbit around the sun. And this is why we have hemisphere-specific difference between summer and winter. So Hong Kong is located in the northern hemisphere, and now is winter. How about the southern hemisphere? So for Australia, it is now summer. Okay, so we have hemisphere-specific difference, and it is because of this tilting angle. Okay, so let's study more why this tilting angle will create weather, or it's not weather, will create climate. Okay, so this is the orbit, okay, the orbit of the Earth around the sun, and we have the tilting angle, okay, the Earth tilt by 23.5 degrees, and we are about here. Okay, we are about here. I mean, this is now December or okay, March. March should be here. Okay, March. So first of all, let's talk about winter. Okay, the winter in northern hemisphere. Okay, for December. For December, you may aware that the pole-to-pole axis, okay, or maybe the North Pole. Okay, the North Pole is pointing away from the sun. Okay, the sun is over here, and the pole, the North Pole, is pointing away from the sun. And comparing to June, okay, comparing to June, this is the North Pole, and the North Pole is pointing towards the sun. Okay, so it means that when it is in June, the northern hemisphere will be more tilted to the sun, and the sunlight will be received by the northern hemisphere in a higher elevation angle. That is more from above our head. Okay, the elevation angle of the sunlight will be higher for the northern hemisphere when it is June. And in December, the North Pole is pointing away from the sun. So for the northern hemisphere, the sunlight will be received by the northern hemisphere at a lower elevation angle. So let's take a look at this section. Okay, we are in the northern hemisphere, and when it is June, the sunlight will be hitting the northern hemisphere at this angle. Okay, at this angle, comparing to winter. Okay, December, for the northern hemisphere, the sunlight will be coming at this angle or this angle. So you can see that in June. Okay, in June, this angle, this sunlight angle will be more perpendicular, right? Will be higher. The elevation angle of the sunlight will be higher comparing to the elevation angle of the sunlight in December. And that's why in June it is summer, and in December it is winter in the northern hemisphere. Okay, how about March and September? When the Earth revolves to March, this pole-to-pole axis is neither tilting towards or away from the sun. Okay, if you draw a line from the sun to the Earth, this line is actually perpendicular to this line. Let me draw it once again. Okay, if you connect a line from the sun to the Earth, then this axis, the pole-to-pole axis, will be perpendicular. Okay, this is a right angle, will be perpendicular to the line joining the sun and the Earth. So it means that the pole-to-pole axis is neither pointing to or away from the sun. So for that, for March and September, the axis is neither pointing towards nor away from the sun. Then it is spring and autumn. Okay, it is spring and autumn. And the Earth will be like this. And on these 2 days, the sunlight will be hitting the equator. Okay, will be hitting the equator. So this is the pole-to-pole axis, the North Pole and the South Pole. And on these 2 days, in the March and September, where the pole-to-pole axis is perpendicular to the line joining the Earth and the sun, the sunlight will be hitting the equator perpendicularly. Okay, like this. Okay. So during May, June, July, the North Hemisphere is tipped towards the sun, okay, pointing or tilting towards the sun. And so it is exposed to more direct sunlight, and that's why they are summer in the Northern Hemisphere. And for the Southern Hemisphere, in November, December, and January, the South Pole will be pointing towards the sun, and it will be their summer. So it is the Earth's axial tilt that caused the sun to be higher in the sky. Okay, higher in the sky in the summer or lower in the sky in the winter. So these 4 days are special. Okay, on the day where the North Pole is most pointing away from the sun. Okay, on this day where the North Pole is most pointed away from the sun, we call this the winter solstice. Okay, the winter solstice. And on the day where the North Pole, which is most tilted towards the sun, we call it the summer solstice. Okay, so for the summer solstice will be around 21st of June, and for the winter solstice it will be around 21st of December. And for spring, okay, on the around March 21st, it will be the spring equinox. And on around 21st of September, it is called the autumn equinox. And the name equinox, like equal, right? The word is like equal, and it is because on these 2 days, we have equal length of daytime and nighttime. 12 hours of day and 12 hours of night. Okay, on the 2 equinox, spring equinox or autumn equinox, we have equal length of day and night. How about winter? How about winter solstice? For winter solstice, we have longest nighttime and shortest daytime. In the contrast, in the summer solstice, we have the longest daytime and the shortest nighttime. Okay? So you can imagine if you are in the North Pole. Okay, if you're in the North Pole and it is the day 21st of June, 24 hours you will not be able to see the sunset. You have 24 hours of daytime. And on the 21st of December, if you are in the North Pole, then once again, you have 24 hours of night time. Okay, not daytime, but 24 hours of night time. Okay, so if you want to see the aurora, you better go in the winter, or you better go in December, November. Okay, you will not be able to see the aurora in the summer. Okay. So in the summer, the sun rises in the northeast. Okay, so that's the characteristics for northern hemisphere. Okay, for northern hemisphere, in the summer, the sun will rises from northeast. Okay, not east, but northeast. And then at the noon time, the sun will be almost above our head. Okay, above our head. And when it is sunset, the sun will set in the northwest. And in the winter sun rises in the southeast. And when it is noontime, the sun will not be directly above our head, but at a lower angle in the south direction. And when it is sunset, it will set in the southwest direction. Okay? At noon solar time, the sun will be straight ahead and the vertical stick casts no shadow. And this is only for equator. Okay, this is only for equator. If you are in the equator and the date is 21st of March or 21st of September, then at noontime, at solar noontime, a vertical stick will have no shadows. Okay, a vertical stick will have no shadows. So this is the characteristics of these 4 particular dates in a year. Okay, 4 special dates. I want you to remember what are their characteristics. Okay, on the winter solstice, we have the longest night time and the sun will be in the south. And in the summer solstice, we have the longest daytime, and the sun for most of the time will be in the north. And for the equinox, for the two equinox, we have equal daytime and nighttime. And if you are in the equator, there will be no shadow at the solar noon because the sun will be directly above our head. Okay, this is what I want you to remember. And next, the sun path. The sun path describes how the sun moves across the sky. So of course we know that it is not the sun moves around us, it is the earth moves around the sun. Okay, but relatively we want to describe the sun path as a way that the sun moves across the sky. Okay, so the sun path across the sky would depend on the latitude of the location. So for Hong Kong, the latitude is north 22.3 degree. Okay, so if it is in the equator, then it will be 0. And for Hong Kong, it's 22.3 degree north. Okay, 22.2 should be 22.3 anyway. Okay, you can check the most accurate number. Okay, and here we have 3 sun path diagram. This one is 50 degree north, and this one is for equator, and one is for 90 degree north. That is the North Pole. Okay, this one is for the North Pole. So let's study how the sun moves across the sky. For 50 degree north, when it is winter, okay, when it is winter, the sun will rise from the southeast. When it is noon time, the sun will have a low elevation angle. Okay, a low elevation angle. And when the sun sets, it will set in the southwest. Okay, this is the winter sun. Okay, winter sun. And then this is the equinox. On the 2 equinox, the sun will rise exactly from the east. Okay, no matter it is 50 degree north or 22 degree north, on the 2 equinox, the sun will rise exactly from the east direction and set exactly in the west direction. Okay, so from the primary school, we learned that the sun rises from the east and sets in the west. It is not always true. It is true only for 2 days in a year. And these 2 days are the spring equinox and the autumn equinox. Okay, so on these 2 days, the sun rises from the east, and then for 50 degree north, when it is solar noon time, the sun will have a elevation angle which is higher than that for the winter solstice. Okay, for Hong Kong, on the 2 equinox, the sun will be quite high. Okay, quite high in the sky when it is noon time. And the sun will set in the west, exactly the west direction. And then next, this is the summer sun. Okay, for the summer sun, the sun will rise from northeast. And then when it is noon time, it has a even higher elevation angle. And it will set in the northwest direction. Okay, so from the length of the sun path, you can guess that in the summer it has a longer daytime, and in the winter it has a shorter daytime, right? The length of the sun path is shorter, so it goes that the daytime will be shorter in the winter. Okay, How about in the equator? If you're in the equator, once again, we have the winter and the summer sunlight. So whether it is summer or winter, because for the equator, we don't have a very clear change of climate. Okay, so like in Singapore, it's always tropical climate, always very hot. Okay, so on the equinox, still it will be the sun will rise from the east, and then the sun will be always along the vertical plane in the east and the west direction. Okay, so when it is noon time, it is directly above our head. Okay, so 90-degree elevation angle, and then it will set exactly in the west direction. Right, so how about in the North Pole? In the North Pole, when it is summer, or maybe I should say in June, okay? In June, there will be 24 hours daytime, no light, no nighttime. Okay, 24 hours daytime. And in the equinox, on the 2 equinox day, the sun will be moving along the horizon. Okay, we'll be moving along the horizon, not rising, not setting, but 24 hours moving across the horizon. Very strange, right? And how about winter in December? In December, the sun will be below the horizon. So you will not be able to see the sun in December when you're in the North Pole. Okay, so 24 hours nighttime. Okay, so this is the sun path for different locations in the world, and I think we will focus on the northern hemisphere. So you see 50-degree north and then the North Pole, and actually for the southern hemisphere, it is just the other way around. Okay. Sun path. So when we want to describe how the sun moves across the sky, then we want to locate the sun. Okay, so like on today is 5th. Okay, 5th of March, and the time 3 o'clock. Where is the sun? I want to locate the sun. Where is the sun? For a location on Earth, we use the coordinates, right? We will use the coordinates of how much degree north and then how much degree east or west. So similarly, for the sun, we also use a coordination system, and we are using 2 angles to locate the sun. Okay. In order to describe the sun's position, location relative to a point accurately. So relative to a point, it will be relative to a point on Earth, like for my window. Okay, the point is my window. We need a coordination system. So a system of angular coordinates is used to define the sun's position in the sky. And once again, the sky is treated as a hemisphere. Okay, we treat the sky as a sphere. And the point will be the center point of the coordination system. Okay, so relative to a point, where the point is the center of the coordination system, we use 2 angles to locate the sun. And those 2 angles are solar azimuth and solar altitude. Okay, so this is the solar altitude. And actually the solar altitude angle is like the elevation angle. Okay, the elevation angle. So it is measured along a vertical plane containing the sun. Okay, this is the vertical plane containing the sun. Okay, it is perpendicular to the ground. Okay, perpendicular to the ground, and it is measured from the horizon. Okay, measured from the horizon. So it means that if the sun is here, when the sun is just rising, or when the sun is setting, then the altitude angle will equal to 0. Let me write it down. Okay, when the sun is rising or setting, the solar altitude angle will equal to 0. Okay, 0 degree. And similarly, when the sun is directly above our head, when the sun is directly above head, then there will be no shadow for a vertical stick. Then the solar altitude angle will equal to 90 degree. Okay, so this is the elevation angle. It is to measure how high is the sun in the sky. Okay, so when the sun is at the zenith, okay, directly above our head, then the altitude angle will be 90 degree. Okay, this position is called the zenith. Okay, on the top of the sky hemisphere, it is called the zenith. All right. Apart from the solar altitude, we have another angle which is called solar azimuth. And the solar azimuth angle is to tell which direction is the sun, whether the sun is in the east or south or west or north. We use the azimuth angle. Okay, so it is about the direction. Okay, about the direction. There are different measurement methods, or I should say, the azimuth angle can be measured from the south, can be measured from the north. So there are different systems to define the azimuth angle. And for this subject, let's fix to one system where the azimuth angle is measured from the south. Okay, measured from the south angle. Compass bearing, yes, it is similar to the compass bearing. Okay, measured from the south angle, and then we have positive and negative. In our convention, we have negative values when, maybe I should write here. Okay, when the sun is to the east, the angle will be negative. And when the sun is in the west, the azimuth angle will be positive. Okay, so like here, the sun is over here, and we will measure the azimuth angle from the south direction to the vertical plane. Okay, to the vertical plane containing the sun. Okay. So we are measuring on a horizontal plane. Measure from the south, okay, on a horizontal plane, and the angle until it touch the vertical plane containing the sun. Then this angle is the solar azimuth. And we have positive and negative. To the east, negative. To the west, positive. Okay. All right, so next we have the Sunpach diagram. This is a very interesting diagram to me, okay, because from this diagram I can tell when is the sunrise, when is the sunset in Hong Kong. Okay, this is a Sunpach diagram, especially for a location of 22.3 degrees north. Okay. if you are in Singapore, okay, near the equator, or if you're in Australia, if you are in London, don't refer to this sunpath diagram, okay, because this sunpath diagram is only for 22.3 degree north, not necessarily Hong Kong, okay. When the latitude is 22.3 degree north, then you can use this sunpath diagram. Okay, so this diagram is called the stereographic sunpath diagram. And on this diagram, we plot the sun path on some dates in the year on this diagram. So from this diagram, we can read the two angles of the sun, solar altitude and solar azimuth, from this diagram. Okay, so let's have a, so the two angle is the solar azimuth and the solar altitude. So how to read? Remember, this is a coordination system, right? So for a coordination system, we may have x-axis and then y-axis, and we can draw some line to represent a coordination system, right? So similar to a rectangular coordination system, we may use an angular coordination system to draw all the line representing these two angles. So in the polar coordination system, these circles will represent the solar altitude. Okay, will represent the solar altitude. So it's just like, let me erase these. It's just like I have, okay, one point. Okay, this point represents a solar altitude angle of 90 degrees. And then I have this big circle representing a solar altitude angle of 0. And I may have another circle. Okay, this circle representing a solar altitude angle of how many? Maybe 20. Okay, and then another circle representing a solar altitude angle of let's say 60. Okay, so these angles, these solar altitude angles, for any point, okay, for any point along this line, we have the same altitude angle. So on the polar coordination system, okay, on a polar coordination system, we may use these circles to represent the solar altitude angle of 0, 20, 60, and then maybe 80, and the center point will be a solar altitude of 90 degrees, right? So it's just like we compress, okay, we compress these circle onto the ground, okay, onto the horizontal surface, and it becomes these circles, okay? So on the sun path diagram, these circles, okay, these circles would represent the solar altitude angle. So here, 0. 0 degree will means any point on this big circle will have a solar altitude angle of 0. And similarly, any point along this circle will have a solar altitude angle of 10. Okay, and all the way to this circle where the altitude angle is 80, and the center point, okay, only one point will have the altitude angle of 90, and this is the zenith of the sky hemisphere. Okay, so we have these angle for solar altitude. All right, how about the azimuth? For the solar azimuth, they are like the compass angle, right? So we have east, west, south, and north. And remember, for the solar azimuth, it is measured from the south. So for the south direction, we have 0 degree. For the east direction, we have negative 90 degree. For the west, we have 90. And for the north, we have 180 or negative 180 degree. And using the same theory, we may have other compass angle, like here, maybe south, east, then the solar azimuth will be negative 45, and then here we have 45, and here we have 135 negative. Okay, and here 135 positive. Okay, so these are solar azimuth. Okay, these are solar azimuth. And why not use the north as 0? So there are different systems. So there is also a system which use north as 0 degree. Okay, so it's just a matter of which system you are using to define the solar azimuth. Okay, so conventionally, for this kind of stereographic sunpath diagram, the south is the 0. I don't know why. This is just the custom. Okay, and so as we mentioned, these angles are the solar altitude, and then along the compass direction, these are called the solar azimuth. Okay, 0 degree means the south, and then negative 90 means the east, positive 90 is the west, and 180 or negative 180 will be the north. Okay, so we have the whole sky. Every point on the sky hemisphere can be located on this sunpath diagram. And then on different dates in the year, we may plot the sun path on the diagram. Okay, I know that the text on the PowerPoint is quite small, so you may need to zoom in to see clearly. Okay, so here, if you can read closely, you can see that this line is actually representing the date 22nd of December, okay, which is the winter solstice, okay, which is the winter solstice. So on this date, where will the sun rise? For sunrise, okay, for sunrise, the solar altitude angle will equal to 0. Okay, sunrise or sunset, the solar altitude will be 0. And we know that the sun will rise from the east, right? So this point is when the sun rising, okay, just rise above the horizon. So the solar altitude will equal to 0. Okay, and then you may be aware that there are some curves. Okay, there are some curves, and these curves are the hour line. So they show the hour, and these hour are the solar hour, or we call it the solar time. I will explain what is solar time later. Okay, so we have 6 o'clock, 7 o'clock, 8, 9, 10, 11, and then noon. So this line will represent the solar noon time. Okay, so the red line shows the sun path on the winter solstice, 21st or 22nd of December. Okay, and then on different time, we can locate the sun in the sky, like 10 o'clock. Okay, let's use an example of 10 o'clock. Okay, on 22nd of December, when it is 10 o'clock in the morning, what is the solar altitude? Can anyone tell me? You can type in the chat box, what is the solar altitude at 10 o'clock on 22nd of December. So referring to the coordination system, it will be around here. Okay, so this represent maybe around 38, 37 degree. Okay, so this is the solar altitude. And if the sun is over here, okay, on 22nd of December, 10 a.m. solar time, then this altitude angle will be around 37 degree. This is the solar altitude on this particular time on 22nd of December. Okay, how about the solar azimuth? What is the solar azimuth? For solar azimuth, it is the compass angle, right? For the compass angle, we may join, we may use a ruler. Okay, we may use a ruler to join the center point to this point and then extend to the outer angle. So this angle, it will be about how much? Maybe 38, okay, maybe around 38, then it means that the sun will be in a, so let's say this is the south direction. Okay, we have south, we have north, and then this angle will be about 38 degree measure from the south. Okay, so this is how we can locate 41. Let me erase everything. Okay, the mark for 40 is missing. How come? So I think 40 will be around here. Okay, 40 around here. So let me use a ruler on the monitor. It will be okay, joining this line and 10 o'clock, joining this line and 10 o'clock. It will be like this. Okay, I cannot draw it properly. Okay, but okay, 30 to 40. Okay, around 30 to 40, around 40. Okay, anyway, so this is how you find out the solar azimuth angle. Okay, so when you are doing it on a paper, it will be easier for you to draw the line. Okay. So we have the winter solstice. Okay, so this is the winter solstice. And we have the summer solstice, which is 22nd of June. How to find solar altitude angle? Okay, so let's go back to the previous example. Okay, I want to find out the solar altitude angle at 10 o'clock on 22nd of December. Okay, on 22nd of December. So this point, this location is between, okay, is close to this coordinate lines, which is representing 40, right? This line is representing a altitude angle of 40 degree, and it is also close to another altitude angle, which is 30 degree. All right, so this point is between 30 to 40. So it means that the solar altitude angle will be between 30 to 40. But because there is no other line, so we can only guess the altitude angle. So it should be closer to 40, right? So this point is closer to the 40-degree altitude angle. So I guess it will be around 37, or now maybe I think it is 36. Okay, so this is how we read the solar altitude angle. Did I get your answer? Did I answer your questions? Okay, so these lines are used to trace back the solar altitude angle. All right, okay, so you may use these concentric circle as some reference line for you to guess what is the solar altitude angle. Okay, so if okay, now in Hong Kong, okay, I want to know when will the sun be directly above my head. Okay, when the sun is directly above our head, the solar altitude angle will be 90, right? So at the center point of the coordination system, it has a solar altitude angle of 90. So the date will be between 22nd of June and 25th of May or 20th of July. So around early June or late June. Okay, early June or late June, when it is solar noon time, the sun will be directly above our head. But when it is solar solstice, when it is equinox, or okay, when it is summer solstice, okay, when it is the summer solstice at noon time, okay, at noon time, you may want to zoom in. This is the most zoom in. Okay, at the solar noon time, the solar altitude is not 90, maybe around 88. Okay, maybe around 88 degree at the solar on the solar solstice at solar noon time. Okay. How about the equinox? The equinox will be poor drawing. Okay, on the equinox, it will be this line. Okay, this is the sun path for the equinox, and you will see that there are two dates. 22nd of March and 22nd of December, because for the sun path, actually the sun path will be oscillating, okay, swinging between north and south and north and south in the year. So in the winter, okay, the sun path is here. Okay, we have winter, and then January, February, and then March, and then April, and May, and June. Okay, so June, we have the summer. And after June, we have July, and then August, and September, October, November, December again. So the sun path will be oscillating. Okay, will be oscillating from south to north and then from north to south. Okay. So here one sun path actually represent two dates. Okay, like this sun path, it represents the date of the two equinox, 21st or 22nd of March and 22nd of September. Okay, so on these two dates, on the equinox, the sun will rise exactly from the east, so that the solar azimuth is 90, negative 90. And the sun will set exactly in the west, the solar azimuth 90 degree. Okay, and when it is noon time, the solar altitude. So can you tell me what is the solar altitude for the solar noon time on the equinox? Let me do a polling. Okay, I give you several answers. Okay, my question is, what is the solar altitude on equinox at solar noon time? Okay, maybe the first one is 30 degree. Okay, and then we have okay, maybe 35. Okay, and then okay, we have 68 degree, and then maybe we have 75 or maybe 76. Okay, just 3 answers. Can you tell? Can you tell me what is the solar altitude angle on equinox at solar noon time? That is the point where I highlighted in orange. What is the solar altitude? Okay, so let's see how to find out the solar altitude. So for the solar altitude, we may use this line, and then we can draw a concentric circle over here. Okay, so if this is 60 and this is 70, then this point will be about 68. Okay, so the best answer should be 68. Okay. And I have when I read this Sunpach diagram, I always use the term solar time. So why I use solar time? Let's take a break. Okay, let's take a break of 5 minutes. I need to stop the recording because I have recorded for over an hour. Okay, so after the break, we will learn what is the meaning of solar time and is it the same as the clock time. Okay.